All right. So good evening. Welcome to the public talk. It will be given by Bojan Mohar. Is it correct? So Bojan Mohar, he is a Slovenian and Canadian mathematician, dividing his time between Simon Fraser University in Vancouver and University of Ljubljana, where he is associated with Institute of Mathematics, Physics, and Mechanics. So, and in Canada, he holds Tier 1 in graph theory, Canada Research Chair. Bojan graduated in 1986. His advisor was Tomasz Pisinski, if I get it right. So his area of research can be described as graph theory, but quite broadly understood, because Bojan is interested in connections of graph theory both to classical mathematics, like topology or algebra, and more applied aspects connected to the theory of computing. I hope we will see both these trends in our talk today. So he is the author of very influential book, Graphs on Surfaces. This about topological graph theory. So Bojan is a recipient of several awards. So I can mention here Boris Kidrick Award in 1990 by the Slovenian government, and also another award by the Royal Society of Canada for more applied stuff, as far as I understand. So he's a member of Slovenian Academy of Engineering since 1999. He is SIAM Fellow since 2018 and American Mathematical Society Fellow since 2020. And he will talk today about crossing numbers, which is a very exciting topic. So Bojan, you have the floor, and let me know that this time the floor is actual floor. It's not virtual, which is very nice.
Right. Thank you, Sasha, for this nice introduction.
You're in charge.
It's my pleasure to open this talk, which is a hybrid talk. So after a year of being home and only trying to do online talks, this is a hybrid. So I have a little audience here. Actually, I'm quite pleased with the audience, and I hope there is some additional audience online. Today, I will speak about crossing numbers of graphs. This is an area which is quite combinatorial, but it has relations not only to several applications, but also to mainstream mathematics. And I would like just to do some brief introduction into this area. It's a public talk, so that's why I will not go into a very technical stuff. I will try to stay low with definitions and keep the theory not too complicated, so for the audience to follow easily. So I will start just to introducing basic objects of this talk, and I want to go with the old conjecture, which came out of art intentions of Anthony Hill, and it's called Hill conjectures nowadays. And then I will describe a little bit about an interesting fact, which is called the crossing lemma and its applications in mathematics, and then continue and coming back to the Hill conjecture later on, after I introduce a little bit of a random geometric randomness and looking at the crossing numbers from a different point of view. So the basic notion here is crossing number of a graph. What is a crossing number? It's so we have given a graph, and which is just a finite set of vertices connected by edges, and there will be one particular family of graphs that I will introduce here. It's a complete graphs, and there is a common notion. So Kn is the complete graph on n vertices. So think of n being either a medium size like K10 or maybe a very large n, so K1000. So having a very large number of vertices, and any two vertices in this graph are connected by an edge. So, and the question is how to draw this graph, or in general some other graph, in the plane, so that to introduce the smallest number of crossings. And this smallest number of smallest possible number of crossings is called the crossing number, CR of G. For instance, if you look at this graph on the right side, it has 20 vertices and it has blue and red edges. And you see in this drawing, I have some crossings of red edges, and I have one red edge here that crosses two blue edges. So this graph has several crossings in this drawing, but there is a different drawing where you can only involve two crossings. Let me just try to show you. You can redraw this edge, which crosses three edges, just maybe going here. And you save. You just have one crossing now, and this edge here you can actually redraw here, and you see once you look at it, it's only two crossings were left, and you can do better. So this is a kind of less trivial to see that you cannot do even better maybe. And so this graph has crossing number equal to 2. Here is a complete graph K6. And you see it has many crossings, but you can do it with 3 crossings. So motivation of this notion came, I mentioned the Hill conjecture earlier in introducing my talk, but also came from a very practical problem. If you think of a graph as a layout for an electrical circuit, and you want to print electrical circuit on a planar board, you don't want many crossings of the edges, because this makes technology difficult to implement. And so very originally, maybe 40 years ago, a lot of effort in crossing number theory was because of this optimization of designs of electrical circuits. Very large circuits were using the notions which came from this theory. Now, one more notion that I will be using throughout my talk is whenever you see n, this is an integer, and this will be the number of vertices of a graph. So n is always, for me, will be the number of vertices. If I forget to mention, this is the number of vertices, and that's what we are gonna look at. And I'm interested when n is large. So what happens when n is large? So we know everything when n is 5 or 6 or 7, but when n is large, that could be difficult. So here you see a different drawing of 2 graphs of K5, complete graph on 5 vertices. It has only one crossing here. There's only one crossing, and the red graph on 6 vertices is complete graph on 6 vertices, and you can see 3 crossings here. So this justifies that the crossing number of K5 is at most 1, and it is well-known fact that the complete graph with 5 vertices cannot be drawn with no crossings, without any crossings. So that's this is actually the smallest graph which cannot be drawn crossing free in the plane. It's a little exercise for a mathematician to prove that K6 needs 3 crossings. Now, Anthony Hill conjectured back in the 1950s that the following formula describes the minimum number of crossings of a complete graph on any number of vertices n. So here you have n minus 1 divided by 2, and then you take the the floor, which is the you just round down if this is not an integer. So if you check for if n is 6, you get 1/4 of. So this is 6 divided by 2 is 3, and then 5 divided by 2 is 2, and 4 divided by 2 is 2, and so on. So and you get that the crossing number of K6, it's actually 3 from the formula, and this formula has been proved. So this is known for every n which is at most 12. And it's, despite many people working on it, it's still unknown if K13 really needs this number of crossings. It is even unknown if this formula holds asymptotically. So if you just think of n being very large, you can forget about this rounding down. So you get basically 1/64 times n to the 4. It's the right number of crossings up to a smaller order terms. So this little o of 1 means a tiny little number when n is large enough. So this is always asymptotic with respect to n. And I will also use the other version. This will come when we will speak about probabilistic versions. This is the same as 3/8 times n choose 4. N choose 4 comes because you can say, okay, I'll choose 4 of the vertices and then I look if they make a crossing or not. So that's, you can somehow use this language, and then this is the handy number. So just remember this 3/8 for the time being. Now, Anthony Hill, who came from this to this conjecture, he was actually a British painter. It's he became obsessed with this problem because he was trying to design drawings of objects which look like complete graphs. For us today, it's a complete graph. So for him, it was like joins of balls, maybe 6, 7, 8 balls, and join them together. So he would need to draw under and over for the joins joining them, and that would be representing the crossings of this. And he came eventually with this formula, with trying to do it, and published later a paper together with Harari, and even later published several other papers with Guy, a Canadian mathematician. And Anthony Hill just died last year, so just last November he died. He was age 90, and the Guardian, the British newspaper, wrote that he was an artist and a mathematician and a writer, and he was a member and actually one of the leaders, theoretical leader of a constructionist group of. This was a geometrically abstract paintings that were that was in England back in the 1950s. So what is this strange number? Where does it come from? It comes from, here is a way how to draw the complete graph with exactly this many crossings. So you can always do it with this many crossings. It's as follows. So think of, instead of drawing in the plane, you can draw it in the topological sphere. Here is the sphere as a cylinder, as a can, for instance. So you can think of a surface of the can. And then you have n vertices, split them in 2 parts, roughly equal. So n/2 and n/2. So one part is maybe a little bit bigger if n is odd. And then you draw the edges between any 2 points in the upper part on the top of this can. And similarly for the lower part on the bottom. So those edges cross, and it's kind of very easy to count how many crossings you get altogether. And then for any point on the upper part to the lower part, you draw a straight line on this boundary, so which is a geodesic on the surface. So you draw a straight line. So you see, if you, I just drew it for 2 points going down, and you see the blue, the red, and the green edges cross themselves. And when you count this, you get exactly the number here. So it's like a magic, but it comes to this very nice number. And the problem of this conjecture, which is still unresolved today, is that lower bound. So why can't I do a tiny little bit better? Can I save one crossing somehow? So that's the Hill conjecture. I'll go on with a little bit more general setup now. And let me describe a very useful mathematical result. It's called crossing lemma. And this crossing lemma generalizes this setup that I have here. So if you look at the graph and try to see if this graph can be drawn with 0 crossings, then this graph cannot have too many edges. So the number of edges, this E of G, this is the number of edges of this graph, is at most 3 times the number of vertices, -6. This comes as a simple corollary of Euler's formula in the plane. So it's a very simple exercise for a geometer to derive this. So if you have one more edge than this, you need a crossing. And then if you have 2 more edges, you need at least 2 crossings. Why? Because think of, now I have a graph and I have 2 more edges. So if I draw it with just 1 crossing, I can remove that one of those edges in that crossing, and then I would have still 1 edge too many. So there is another crossing. And similarly, if I have E of G edges, I can, removing 1 by 1, I still have crossings in any drawing. So this gives the lower bound on the number of crossings. The lower bound is a kind of difficult thing to prove. But this lower bound is good for very sparse graphs, but not for when you have lots of edges in a graph. Paul Erdős actually asked, and what happens if the graph is dense? So how many crossings do you need? He conjectured a formula like this one, which is known as this crossing lemma. And the crossing lemma says that the number of crossings is not linear in the number of edges, but it's more than linear. So it's this number of edges cubed divided by n squared. There is a technical condition if you have enough edges. So if you have fewer than 4n, you can use just this first formula that I showed you. But if you have a very dense graph with many edges, then this is the right number of magnitude. If you think of the complete graph, so for complete graph has n choose 2 edges, so n times n minus 1, let's say about n squared over 2 edges. And so this would give n squared over 2 would be n to the 6 divided by, so it would give about order, so theta of n to the 4 if the graph has quadratically many edges, which is the right amount. So that's the crossing lemma. Crossing lemma has a very nice proof. It was very popular, and it's a one, people say it's a book proof. So it appeared in this book by Eigner and Ziegler in about book proofs, which is an idea which came from Paul Erdős. When it came out, it was a lot of research was done, and János Pach, who is on this slide, who you will see on this slide, he actually had a lot of result and developed single-handedly with many co-authors. He developed so-called geometric graph theory. So it was it's an area which started with this nice crossing lemma. Today, this 1/64 has been improved to 1/29, so that's the best. And it's of course it cannot be improved much more, but it maybe there is still a little bit of room. So when I told you that Erdős asked this question, why would Erdős be interested in these crossing numbers? And there is a relation to number theory. I think that was the main interest which came. So let me describe this, but in a more geometric language about point line incidences. So suppose I have a certain set of lines in, let's say, L lines in the plane, and then I have a set of points on these lines. So maybe some points are on the intersection of two lines, like this one here. And then you can count the number of incidences. So the pairs point lying on a line, one of these lines. So how many incidences you can get? So here is one which turns out to be quite extremal in some sense, as we will see. And it says, let's take a grid, integer grid of points of, let's say, height n, and width n squared. So you have n by n squared points. So the number of points here would be n cubed, n squared times n. And then take all lines like this red one or this green one that contain, you can say n points, but at least n/2 of these points. So you can do this one. You can do, for instance, one from this line that doesn't go, that goes 3 to the right and 1 up. So this would be like this one and this one, and then this one. So it would also cross n of the points in this set. So you see, basically, if you look at the slope, so here it's slope 1, here it's slope 1/2, 1/3. Let me call this a slope. So you get these lines for every such slope up to 1 divided by n, because it's very long strip of n squared. So it's easy to count that the number of lines here, it's constant times n cubed. So you get you have n cubed points through each point you have about n of these lines, and then of course each line uses at least n/2 points. So you get a little bit fewer. You get fewer lines. So it's this is the order is n cubed. So you get n cubed points, n cubed lines, but the number of incidences is order n squared, n⁴. So it's much more incidences than the number of lines or the number of points. You can guess how this could be in use in number theory, for instance. And so we define the incidence function is the maximum possible number of such incidences you can attain with some point set. And what it turns out is the example I showed you, it's almost extremal. So why is that? Well, this is because there is a theorem behind which says that the number of incidences is at most, so this O notation means it's at most constant times L to the 2/3 times P to the 2/3. So it's much, it is at most this. And if you look at the example here, so this is P times L would be n to the 6, and n to the 6 to the 2/3 is just n to the 4. So it is the right, this is the right condition. And Semeredi-Trotter theorem actually says this. Now, Laszlo Sekei came with a beautiful proof of this Semeredi-Trotter theorem. So this theorem, original proof was very long. But here is a couple of lines proof using crossing numbers, and I will show it to you here. So let's suppose I have some set of lines and some points, and then I try to see how many incidences. So you see, for this first point, I will have I have 3 lines through this, so I have 3 incidences and so on. You can count how many there are. But this is just for illustration purpose. So let me try to go with a proof. I will define a graph, G, which has the number of vertices will be just the number of these points. So one vertex for each point. And then if I have one of the lines, I will make the edges on this line connecting consecutive points. So like this one, or let me do one of the green. So this one will be for this line, there will be 2 edges. So between this point and this point, and this point and this point. And this is a crossing here in between. So you see, you get a graph drawn in the plane. It has P vertices, the number of edges of this graph is, you see, if you look at on each line, you count the incidences. So this will be just the number of incidences. But then instead of 3 incidences, I have just 2 edges. So for each line, you subtract 1, so you get minus L. So this is the number of edges of this graph. And let me now write down the crossing lemma. So the crossing number of this graph is at most the number of edges cubed divided by. So the crossing number of this graph is at most 1/64 I cubed. Well, minus L, but this L is typically smaller. So let me just pretend there is no problem. So, well, I can take something bigger anyway, and then divide it by n squared. So if you rewrite this, you get I cubed is, sorry, crossing number is bigger, right? So that was the crossing lemma. I cubed is bigger than 64 times n squared times the crossing number of the graph. But you see, the crossing number is here. The number of crossings is actually cannot be too big because I have L lines, and any 2 lines can only cross once. So the number of crossings is always smaller or equal. So I guess I messed up with the inequalities. So it's this is smaller or equal. So this would be smaller or equal 64 times n squared times the number of line squares, because any 2 lines can cross at most once. And you see, if you take the cube root, you get the I is at most 4 times n to the 2/3 L to the 2/3. So it's this is essentially the Semmelredi-Trotter lemma, and the little terms here serve for when you don't have enough crossings, then you have this as a lower bound. Let me mention that this proof works actually for more general things. You don't need lines. You can have pseudo lines. So you can have everything works the same way. So it's so it's a more general statement than you get it from the lines only. So you see, a crossing number, just the notion enables us to prove a difficult theorem with within a few lines. Now, having explained that, I'll go to the next notion, which comes from an old problem of Sylvester. Sylvester was in the 19th century mathematician, and he asked in 1864 the following question. Suppose you choose 4 points at random in the plane. What's the probability that you get? What's the probability that you get this figure, that you get a convex foregone out of these 4 points? And what's the complementary probability that you get a convex triangle with the 4th point inside? So that's an interesting question, and he published this in a journal, and a year after, the journal collected many answers that came, and many answers came. So this was the state of the art up to here. Oops, sorry, up to Woolhouse. No, even including Woolhouse, I think. So you see, you get six answers, and no two are the same. Well, maybe there were more answers, but 6 different answers. So how could it be? So it's only one answer, but all of them proved it. And essentially, at that time, they didn't have a right notion of what is the random point set. And today we know, because there is no compactness, the whole plane is non-compact. But the proofs given were somehow given like this. Wilson's result holds if you look at the triangle instead of the whole plane. You look at any triangle, and then you say, okay, I choose now 4 random points in this triangle. What's the probability? It's 2/3. So that's the state of the art. And this was actually where the geometric probability started. So based on this simple question, ill-formulated question, many good mathematical things emerged. Now, the Sylvester's question is actually very tightly related to the crossing number, but to a version of the crossing number which is called rectilinear crossing number. Namely, if you think of, instead of the plane, you think of, I put n points in the plane. Let's say this R is just a finite set of n points. Now I choose 4 points at random, and I ask, what's the probability that I get the convex foregone? So if you get a convex foregone, for instance, if you choose these 4 points, you get a convex foregone. Then in the corresponding drawing of this graph, where you draw each edge as a straight line segment, that's why it's called rectilinear. So then you get the crossing. But if you would choose these 4 points, you would get no crossing. So the Sylvester probability essentially gives you the crossing number of a drawing of the complete graph on this point set. So essentially, it just gives you the so-called rectilinear crossing number, because you are bound now to use the straight lines. So that's the rectilinear crossing number, which you can define for any graph. And it turns out that it is a little bit different notion. So it's, of course, if you are bound to use straight lines, you may need more crossings. If you can draw edges curvilinear, then you maybe have a good way to eliminate some of the crossings. So this is this was the Sylvester's question related to the rectilinear crossing number, and this was actually Scheinerman and Wilf find out this relationship, and they proved a nice statement. So let me just from this slide use the notation, this nu star, to be the best possible point set in the plane, or best possible set in the plane where this Sylvester probability is the smallest possible, so it's infimum. So this would correspond to drawings of the complete graph with straight lines. And coming from this, here are today's best bounds for this Sylvester's probabilities in all possible sets in the plane. So there is a lower bound and there is an upper bound. I will expose these bounds in the next slide more vividly, and just remember that this is a recent state of the art. So what do these bounds actually mean? So here are these numbers that I had on the previous slide. So 3.799. This one was on the previous slide. So let me just look at this 3/8. You remember the Hill constant from the beginning of my talk. This was the 3/8. So it is conjectured that the crossing number of Kn divided with n choose 4 is, well, it goes to 3/8 when n goes to infinity. So this is the Hill conjecture here. Now, today we know that by the constructions that the crossing number of the complete graph, this number, it's smaller or equal to this here. So it's somewhere here. Maybe we all believe it's equal to 3/8. But actually, the best lower bound has been just proved just about a year ago, 2 years ago, by Balog, Liditsky, and Salazar. They proved that this actually 3/8 is right up to almost 1%. So this is the lower bound. So this was proved. So this is proved. So Balog, Liditsky, and Salazar, they used so-called Flach algebra calculus, which is essentially due to the chair, to Razborov, to the chair of this talk. And it's also a variation of graph limits inequalities that introduced by Latsilovas about the same time. So this work gave this as a lower bound, and then we know that this ratio tends to some number in between these two. Now, if you look at the rectilinear crossing number, the story is different. Then the quotient goes to some number, something in between these two values. And again, this is pretty recent, and the breakthrough in this area was actually a paper by Lovas, Westergombi, Wagner, and Welzel. They proved in 2004, they actually proved that this limiting value for the rectilinear crossing number of complete graphs is strictly bigger. So they proved like 3/8 plus 0.001. They proved just tiny little bit bigger, but still it was a lower bound. That was the first one. And then later it was again using the Flach algebra methodology, the better bound were found. So this is the state of the art of this Hill conjecture and related conjecture. So here we have a conjecture, but for this one, we don't know really what the right value is. Is it the lower or the upper one here? Which one is the right one? Now, if you look at the plane and then look at the rectilinear drawings, you can as well try to do on another sphere, do rectilinear drawings on the sphere. So let's take, instead of looking drawings in the plane, we can look at the drawings on the sphere, and then we can ask, oh yeah, what if I take 4 random points on the sphere? What's this Sylvester probability? And it turns out that it behaves better. It's amazing, but the positive curvature makes fewer crossings. So that was actually realized back in 1960s by a British mathematician, Moon, who proved that actually if you take a random drawing on this unit sphere in R3 of the complete graph, then the expected number of crossings will be asymptotically the right value, this Hill value, the 3/8. So 3/8 and choose 4. So that's Moon's result. And it's amazing that this holds. So this is, so Hill must be right? Now, here is another attempt. So instead of the sphere, I can take another surface. For instance, let me take the one which I have here, this surface of the cube, and then I take geodesics with respect to this intrinsic metric here on this surface. So what do you think? You get which one? So I take random points on this. Which one will have fewer crossings, the cube or the sphere? Looks like the sphere should have, yeah. But surprise, it's the same. So that's an interesting fact. And then I will try to convince you why this is the case. So that's going to the last part of my talk. And first of all, I want to show you that these Hill drawings that I mentioned on the can, there are actually many more ways to do the Hill drawing. So I will say a drawing of the complete graph is a Hill drawing if it has precisely that strange number. So 1/4 times n/2 rounded down times n-1/2 rounded down and so on. So this many crossings. And here is the theorem. So what I do is I take the unit sphere in R3. So this is this S2. I take a finite set of k points, like this blue and the red and the black point and so on. And then I take, for each point, I take its antipode, minus p. So I take a set of k points and their antipodes, so there will be 2 k points. So here n is 2k. I have it here. I have 2 k points on the sphere. And if this point set is tame, which means the following. So I'll try to do it here on this example. So tame, I will mean that I can join the antipodes with on the great circles. For instance, I can join this one on the great circle. I can join the 2 black ones. Let me just do it here. And I can join the blue ones with another great circle, which does not. So this is just a half circle, and they don't cross each other. So they don't cross. Then I say that this set of 6 points is tame. So if I manage to find such antipodal points and then they are tame, then I just draw the shortest edges possible for this complete graph. Here I have 2k vertices on n vertices, and I get the Hill drawing. I get exactly the same number as the Hill has. And it has additional properties. These drawings have additional properties. It's amazing that such a simple structure actually always works. So what's the proof? Well, here I can show you a proof in a few lines. So you take 2 pairs, 2 points PQ, and then their antipodes. So like these blue and black points. And what they determine is, if you look at the geodesics, joining these 4 points is a cycle of length 4, but it's a great circle on the sphere. So it's a great circle. Now, if I take another pair of points, maybe on the equator, so this will be the antipodes, of course. and these two. So this will be the equator. Then these two circles cross exactly twice. So they make I have 8 edges, but they make 2 crossings, right? So the intersection of this is 2 points, and it has 2 crossings. So that's the message from this part. Now I can go to I can just give you the proof that we get the Hill value out of this. So what do we get? So we have k points, k pairs of points, and then for any 2 of the pairs, so it's k choose 2 possibilities to get 2 of them, I get this many great circles. And then I take 2 of them and another 2 which are just different. So k minus 2 choose 2 possibilities for another pair, and I get 2 crossings out of those. So you just count all these crossings, and what you get is almost, I mean, you get this a number, and then you also need to add that you will need to add the same half circles between the opposite points, and you can count easily how many crossings they give. It is just this number, and you see if you sum up these 2 numbers, you get this, which is, if you think of n is n over 2 is k, you get the same value as here. So this is the Hill value after. So for when n is even, it's this value. It's the Hill value. So 5 minutes you can explain the proof, even the counting, and it's a beautiful counting argument that gives exactly the Hill value. So that's a surprising result. Let me show you one more proof, and I know I'm close to the end of my time, but still I will be able to prove one more theorem, and essentially the following one. So suppose that I take, you remember Moon result. Moon showed that if you take uniform distribution on the sphere, then you tend to get drawings which are asymptotically have the right number of crossings. So that was this result of Moon from the back of 1965. Now, instead of uniform distribution, you can take any distribution, any probability distribution on the sphere, as long as it has the property that it's antipodally symmetric. So antipodally symmetric means that taking one point here is the same probability as taking a point in the antipodal point. Well, you cannot say the point because it's not a point measure, but this is just a definition of antipodally symmetric. And then you want some non-degeneracy condition that assures that you don't get many points on the same great circle, which would not. And then we can show that. So this is a work with my student Alexandra Vesolek, that the result of Moon generalizes to this setup. So this is the setup. So we have this non-degenerate antipodally symmetric probability distribution measure on the unit sphere, and then the expected numbers of crossings, if you choose mu random points, is the right value as conjectured by Anthony Hill. So here is the proof. It's faster than even stating the theorem. So it says something about probability. It says about probability distributions, but the only ingredient in this proof which uses probability is just coin flipping. So here is the proof. It's you see it's 3 lines. First thing is that because this is non-degenerate condition, then this means that we get if we choose n random points with respect to this probability measure, they will be in general position. So no 2 will be antipodal, no 3 points will be on the same circle. Now, antipodal symmetry says that choosing a a point with respect to this is the same as choosing a pair of antipodal points and then remove one. So I can do it, just think of differently. This is the same way. So I can say, instead of choosing one point, I will choose pairs of points. And then I will randomly remove them. So when I choose pairs of points, remember my previous construction of these hill drawings, you get a drawing which has this optimal number of crossings, the minimum, conjectured minimum. And now I delete from each pair, I delete one of them. So what happens when I delete one of them? Well, you see, if I had a crossing before, it involved 4 points, P, Q, and some A and B. And this crossing will survive with probability 1/16 because it is the same as not keeping all these 4 points. So each point I remove, there was P and minus P. I remove P with probability 1/2. And so that's so the probability of that this crossing survives is 1/16. And before I had roughly 2n to the 4 crossings then times 1/64. And now I will have the same number, but only in average, only 1/16 of them, which just gives n to the 4. And that's precisely the result. So it's a beautiful result, and I consider such a result. I started with the art of Anthony Hill, and this is for me this is like a poetry in mathematics. So you get a result which about probability distributions where you're only flipping one coin. So that's and you can prove this in 3 lines. This is where I want to stop, and thank you for your attention.